Hello, my name is Sergio Ammirata, and welcome to RIST Ground Control to Major Cloud. This will be a tutorial or a template on how to deploy and use LibRIST for a ground-to-cloud live video transmission. We're going to be covering several topics. First, we're going to have an explanation followed by a demonstration on how to clone, compile, and deploy LibRIST in a fresh EC2 AWS Ubuntu image. Then we're going to discuss some cost-saving strategies for these deployments. Here's a diagram of the cloud deployment we are going to talk about. It consists of one desktop machine, the Fedora Linux, and two AWS cloud machines. One of them is a standard Ubuntu server, and the second one is an instance of our media server. Step one, we're going to grab a file and stream it using UDP unicast to the local adapter on the Fedora desktop. Step two, we're going to receive that stream using LibRIST resender utility, and we're going to send it out towards the cloud. Step three, we're going to receive that stream using LibRIST receiver in an Ubuntu cloud machine, and we're going to forward that stream using UDP unicast to another cloud machine that has our media server. Step four, we grab that UDP live stream at our media server, and we turn it into a WebRTC resource for anyone to play. We will see that all this can be configured in under 6 minutes. So let's describe the steps first before we move to the live video demonstration. First we log into AWS and we go to the public AMI image area to find the appropriate Ubuntu installer for the cloud machine that we want to get, instantiate. When we get there, however, we realize that there are over 130,000 public images, and several hundred of them are Ubuntu options. We need a better strategy to find the correct Ubuntu machine. So what we do is we go to Ubuntu's site. They have an image locator to help you find the correct AMI ID that we're going to basically copy and paste into AWS. This is what this page looks like, the Ubuntu locator. In their page, we specifically filter by region, by version, we want Ubuntu 2004, and by architecture, we're going to do our test in a 64-bit Intel machine. Once we get the correct AMI ID, as you can see here, we're going to go back to AWS, the user interface, and we're going to find that say AMI ID there and use it. Once we find the AMI, the correct AMI on AWS, we're going to choose a launch action, which basically starts the process of instantiating our Ubuntu machine. This is what the interface looks like once you have narrowed down the AMI to a single one and are about to select the launch action from the menu on AWS. The next step in the process, once you click on launch, is to pick the machine size. LibRIST uses very little resources, and you can get away with using the T2 Micro free tier that has only one virtual CPU. However, if you expect bursts of large packet loss, we recommend you use a larger multi-virtual CPU machine in order to guarantee a jitter-free stream out. In our test, in our demo, we're just going to proceed with a free tier. The next step in the machine creation process is to adjust the AWS Firewall to allow the RIST UDP transmission into the cloud. You can use any port of your choice. However, we recommend you do not use ports below 1,000 as they are typically reserved for other system services. Here's the AWS interface for configuring the security groups. As you can see, we added a rule to open a range of UDP incoming ports, and we're going to use that for our RIST traffic. The final step in the machine creation process is the assignment of SSH key pairs. This basically allows you to log into the server that you're creating without having to enter username and password. You basically need to create and import the key only once, and then you can use it, select it from the drop-down on every new machine you create. And this is what the interface looks like at AWS. After this step, the machine will be created, and you will be presented with a summary page of the creation process, which also includes a link that contains the instance ID of the newly created machine. If you click on this link, this is what you'll get. Basically, this is an AWS page that holds all the details of the machine you just created, the Ubuntu machine we just created. The important items here for us are the public IP address and the private IP address. These machines are hosted behind a static NAT. That's why they have a separate local private IP address. So now we're going to go ahead and log into the newly created machine image so we can run all the compilation commands necessary to build and install LibRIST. You can see we just do SSH Ubuntu at the IP address, and we immediately log into the console. Now, in order for us to build LibRIST, we need to install some prerequisites. This looks complex, but it is actually quite simple. All we are doing is installing the compiler, some tools, and a few libraries into Ubuntu, and then issuing the standard, well-documented LibRIST build commands. You can see them on your left. I'm not going to go into detail, and you will see them during the live demonstration. Here are the same instructions specifically tailored to the Fedora desktop as well, because you're going to have to build it on your Fedora desktop as well, or if you happen to use Windows, there are some instructions to do it on the Windows as well. Going back to the Ubuntu Cloud machine, once we have built the LibRIST tools, following those set of instructions, so you can just copy and paste them into the command line, we can verify that everything is working by bringing up the help for either the resender or the RIST receiver, like you see here. So now, let's go ahead and watch a live demonstrations of all these steps performed in real time. All right. Okay, so we start our screen recording, and we go ahead and go into the AWS console. We're already logged in, and we're going to go ahead and try to find, like described, our AMI image that we're going to launch. So we're going to go to the public images, quickly realizing that there's 130,000. We go ahead and use the Ubuntu image locator to track down the proper one. This URL you can find in our presentation. Here, we're going to filter by region. Our AWS account is East 1. We want 2004 long-term build, and we want a Intel 64-bit, which is the AMD 64. So now we have an AMI ID. We go ahead and we copy that ID, and we go back to the AWS user interface and filter by ID to find specifically that one. So it's right there. And now we choose the launch action on that AMI image, which is the installer. We're going to choose the micro, T2 micro, which is a free tier. So you get, the machine will run for free. We edit the security options. We're going to allow TCP SSH from anywhere so we can get into the machine. And we're going to open a range of UDP ports coming in to send the RIST stream. So we go to the next step, and we go ahead and launch the machine, and we select our SSH key pair we already had configured. So the machine is created, and now we have a link to the instance ID. We click on the link, and we get the details. Particularly, we have the public IP and the private IP address of that machine. Here we're editing our cheat sheet, our scripts that we already have ready for copy and paste, and we're replacing the current public and private IP addresses of the machines we just created. They change every time you create a new machine, so we need to edit our scripts accordingly with those new values for this demo to work properly. So now that we have fixed all of our scripts, we can go to the next step. The next step is we copy the public IP of the Ubuntu machine, and we're going to go ahead and we're going to SSH into it using the Ubuntu user. So then we issue the SSH command, and it takes us right in without having to input a password. Next, we're going to go ahead and run the series of commands needed to prepare the build environment. We update the source repositories. Then we install the major dependencies, the compiler, and the libraries. In this case, the libraries are not necessarily needed, but they sometimes give you faster performance depending on the platform, as opposed to using the built-in code for specifically TLS or the LZ4, etc. Once this has finished, we go ahead and we clone the Git repo to get the latest source code base, the latest stable build for the Libris library. And you see here it's about to be done. So we copy and paste the Git command, and that clones the repository. Once the repository is local, we create the build folder, and we change into the build folder. We do a change directory, go into the build folder, and we issue the meson command, which just configures the source code for compilation. After that is done, it's pretty quickly. We compile it with the Ninja command. It's also very quick. After that is done, we go ahead and we install the library and the tools. And we run a command to register or refresh the libraries in the OS, which is the ld-config. Now that is done, we verify that everything's working by running resender with the help. Or if we want to see the URL help, there's another -help-URL for that. So now we're pretty much ready to start our test. First step, we grab a standard video file from our machine, and we run a VLC command that turns it into a UDP stream on a loop, just to create a simulated source. In your case, that source may come from somewhere else, like a video camera or some other. Right now, we're verifying that our source is working by using a standard VLC GUI to open that stream, which was directed to the local adapter on port 8194. So we can see the video stream that we created from a file is working. It's about a 3.5 megabit per second stream. It's 1080, 2397. So it's a pretty decent, pretty standard video stream. The next step then is to grab and read that stream using the resender. And we read it from the local adapter 8194, no encryption, and we're going to send it to the cloud, which is the IP you see there, the 18206, etc. We make sure we put enough bandwidth to hold our stream for our internal QoS, and we set out other parameters like the buffer size, etc. That is beyond the scope of this presentation, the explanation of those parameters. So on the receiver side, we're going to have the RIST receiver listening to the appropriate port, and then forwarding the information to another machine within the cloud. We have to make sure that the parameters of RIST match between the two, meaning the buffer size, etc. So now we run the receiver on the Ubuntu Cloud machine, we start the receiver, we start the sender on the Fedora desktop, and we have some very valuable statistics that we can see during this run process. The next step now is to go ahead and look at the media server, right? The RIST receiver on the Ubuntu machine is sending, after it goes out from the RIST tunnel, it's sending it out UDP unicast to this machine, which is listening on that port 8198. And then its output is configured through our media server to be WebRTC. So it's just doing a conversion. It's not transcoding or anything. It's just converting it to WebRTC. We're going to go ahead and start the service on our media server. And once we start the media server itself and the service that reads the stream, we will go ahead and play it back. On the media server, we need to put the public IP. Since it's behind a NAT, we need to specifically specify what the public IP of the WebRTC stream is going to be. So now we come to the link that was exposed here for the WebRTC playback. We're going to copy that link into the clipboard and use it on a standard web browser. WebRTC can be played on any web browser, whether it's mobile or desktop. It will work everywhere. It's a very nice way to have a ubiquitous way of sending your video stream or broadcasting your stream without having to have a player in anywhere. So here we see, we go ahead and we started on a standard Chrome, and we get the video. It's playing just fine. And that's pretty much the end of our demo. We got the stream in, and we distributed it everywhere using WebRTC, using open source tools. Okay, so now I'm going to go ahead and go to the next slide. Okay, so next steps. We showed a simple workflow in the cloud. We just used the incoming live stream. We piped it to another machine within the cloud that converted into WebRTC. In your case, you will probably have additional steps and more complex workflows. So let's talk about some cost saving strategies now. First, the free tier will work for the RIST receiver as long as your next step in the chain can handle jitter, which will be significant during events of high packet loss unless you have a multi-CPU machine. Second, Libris will also compile and work perfectly in ARM machines. This could save you significant computational dollars, as these machines have a lower price per CPU cycle. Bitstream costs, let's talk about those. Remember that inbound traffic and traffic between AWS machines is always free. So sending the data from the desktop to the cloud and within cloud machines is always free. However, any data coming out of the cloud, for example, in our case, the WebRTC playback, that is going to cost you per byte. So be aware of that distinction. Next, post-processing in the cloud. Another way to say is encoding the stream in the cloud for other purposes. For example, we send one stream to the cloud, and then we have a process in the cloud. It could be our media server or our transcoding engine or somebody else's transcoding engine. You can create your own, and you can create a multi-bit rate output before you feed it to the media server, which can serve HLS or Dash or whatever it is that you need. So by sending the stream once, you're saving the complexity and the cost and having multiple encoders at different bit rates reach the cloud and having to be synchronized. This can be all done within a cloud process. So in conclusion, Libris provides an easy and reliable method for pushing a stream into the cloud that is 100% under your control. Thank you.